Well, let's go over our test review for our reaction types and balancing equations for 2018 through 19. This is part 1. I'm going to do the first page, questions 1 through 12. So, what are the 3 factors that affect the rate, speed of a chemical reaction? Well, let's see. Page 15 in your notebook should go over that. Let's see. We had a reaction rate lab, and I think we also took some notes on page 13, part D, where we talked about those factors that'll do that. And let's see, what are those factors that affect rate? Well, temperature definitely does. High temperature makes it go faster. And stirring. Increase mixing or stirring. The temperature means you're going to get increased kinetic energy of the particles. If you're mixing this in hot water, those particles are just physically moving faster because they've got higher kinetic energy. When you mix stuff, when you're stirring and mixing them up, you're also partially increasing their kinetic energy a little bit. That's part of it. You're also increasing the number of collisions. When these particles collide together, you're just going to get more dissolving. And it also can bring, when you are mixing, it can bring fresh, if it's a water reaction, you can bring fresh water in. You can bring fresh reactants in that haven't had the chemical mixed into them yet. So let's see, we've got temperature, mixing. Oh, and that's going to be the size of particle. Let's see. So, size of reactants. So that means if you get a powder where the particles are really small, they are going to have a huge surface compared to their volume. Whereas a bigger, something like a salt rock crystal dissolving, that is so big, it's going to take a lot longer for this to dissolve because its surface to volume ratio is really low. Even though it's a big looking crystal, when you compare how much volume it has to how much surface area, the surface to volume ratio is really low on this one. These little tiny particles, they're so small, their surface area compared to their volume is huge. So that was an SV, just for surface to volume ratio. But we'll come back to those later. Let's see, we want you to balance the following reactions and identify. Draw arrows showing movement of the atoms. Okay. So for this first one over here, before anything, I'm just kind of looking at the reaction. What type of reaction is that? Well, I've got 2 different compounds or elements. So I got 2 things. I'm just going to circle them for now. An element and a compound. And they're joining up into just one thing. They're joining up into one new compound. So they're combining. That's also known as a synthesis reaction. I'll just put synthesis, that's kind of one of the terms, but you can also call it a combination. What's next on here? Balance and identify. Oh, let's balance here. So I'm just going to do the T-chart method of balancing. Aluminums, we've got 1 over here. Over there, aluminums, we've got 2. So that was going to need to be balanced. As far as oxygen atoms, in that there's 1 molecule of O2, but there's 2 oxygen atoms. And when we're doing this chart, we're doing how many atoms there are. Over here on this side, we've got the subscript tells us there's 3 of those oxygens. So we would recommend, see which element you want to balance last. Well, we're going to balance the O2, the oxygens last. So that was what we'd recommend last. And in this particular equation, the only other one's aluminum, so that's what we'll balance. Oh, wait, I take that back. I'm sorry. We're going to balance the aluminum last. My mistake. If you have a metal or an element all by itself, we're going to balance that one, which means then we're going to balance oxygens. And right away, I can see we've got 2 over here, 3 over there. The least common multiple is going to be 6. I'm going to switch to a pencil now because that's what you should use balancing equations. So I need to get my oxygens balanced now since we're doing aluminums last. And I'm going to multiply this by a coefficient 3 because 3 times 3 is going to be, now we're going to have 9. Oh, wait a minute, my mistake. least common multiple is 6, not 9, pardon me. There we go. 3 times 2 of these molecules is going to be a total of, we got 6 oxygens over here in the products. And over here, since we have 6 over there, we're going to need to balance this over here, the O2s. We only have 2, so we need to put a coefficient 3 in front over here. 3 times 2 is now 6. The oxygens are balanced now. And so now we've got 2 aluminums. Oh, wait, we got to adjust the aluminums, because when I put this coefficient 2 in front, 2 times 2 is 4. I forgot a step there. So we got 4 aluminums over here now in the reactants. Excuse me, in the products. So that means in the reactants we need 4. And that's why we do this one last, because we can put whatever number we need. And now 4 and 4, 6 and 6. If it helps you to visualize this, you know, you could draw this reaction. Now we've got an aluminum, an aluminum, an aluminum, and an aluminum. We got 3 of these little atoms floating around. We're going to have 3 molecules of oxygen. Now they're going to break apart these, they're going to rearrange, usually need some energy, and we're going to end up, for every 2 aluminums, here's 2 aluminums, Al and Al, we're going to have 3 oxygens stuck to those guys somehow. So there's 1 molecule of the aluminum oxide, and now we need another one. Aluminum bonded to aluminum, and those have 3 oxygens stuck to it. So there's our 2 molecules. And let's see, since we are having 2 compounds joining together, oh, we already said that was synthesis, so I think I've answered everything here. Which element should we do first, last? Identify, synthesis. Okay, so we got that one done. This one over here, another practice one. So we've got 1 type of compound breaking down into 2 different types. So when we have 1 compound breaking into 2 different compounds, that's going to be decomposition. Decomp. I'll just abbreviate it. And let's see, balance and identify. Okay, so I've identified it. Let's balance this one. I'm going to make the T-chart if it helps you out. Or actually, I'll try another method here. We got hydrogen and iodine. So we've got an iodine bonded to a hydrogen. I'll make that a little smaller. We practiced drawing these in the last unit. And it's forming 2 atoms of hydrogen bond together. Plus, we're getting those big iodine. Oh, we're getting 2 of those iodines hooked together over there. Okay, so just looking at what I'm going to do is, just to make it easier for this, I'm going to make the iodines kind of a reddish color, reddish color, so we can see those on there. And I'll just try to get rid of the red there by just putting a big H. So visually, if we're looking at it visually now, it's like, okay, we've got over here, we've just got 1 of each, but over here we've got 2 of each. So we need another hydrogen iodine over here. Now we can do that mathematically by putting the coefficient 2 in front. I'll put parentheses around, which means now we've got to have 2 of those hydrogen iodides. So I'll draw another hydrogen, another iodine one over here. Go back to my pencil. So it helps you to visualize. Now let's see now. We got 2 iodines in the reactants. Oh, over here now, we're not, so we balanced over here. Oh, I goofed up. See, that should be 2 iodines. Oh my goodness, I think I'm coming down with a cold. That should have been like this. There we go. Let's see if I got my fancy eraser here. I do. Sorry about that. That's why it's good to do them in pencil. I'm just doing them in pencil from now on. Okay, now that I got these all squared away now, we can see now 2 iodines in the reactants, 2 in the products. We have 2 hydrogens over here. They've combined over there. And let's see, balance and identify this type of reaction. Well, let's see, and we got well, this type of reaction, let's see, what do we've got? We've got a metal bonded to some nonmetals, and it looks like the calcium comes along and takes over working with the chlorine. So what I kind of like to do is the calcium's going to come over here. It's kicking off the aluminum. So, and when this tends to happen, it's going to be a metal kicking off a metal. That'll help you. And so now there's the aluminum all by itself. We've got a new compound, and we've had one element replace another one. That's called a single replacement. Single replacement. And we've got an element and a compound. We're forming a compound and an element. That's one of the ways you can tell a single replacement. Now in this one, what should we balance first? Well, let's look at what we should balance last. Since we have an element here all by itself, we're going to do calcium last. What should you do first? Well, since we only have, we got some aluminum and chlorines. Well, over here, look at this one. The aluminum, there's another metal all by itself. Let's do the calcium and the aluminums last, which means the first one, the only one left to do are the chlorines. And we have got, I'll do a T-chart here if it helps you out. Let's first work with the chlorine. I'm just going to put chlorines for right now. Chlorines. On this side of the reactants, we've got 1, 2, 3 chlorines. Over here in the products, there's only 2 chlorines. So we need to have the same number of chlorines on each side. The lowest number that equally goes into both is 6. So I'm going to multiply this side of the equation by 3, at least the calcium chloride part. 3 times 2 is now 6 chlorines. Over here, I need to multiply, I'm going to put parentheses around this. We need 2 times 3 is going to be 6 chlorines there. Now the chlorines are balanced. Now at this point, I'm not even going to really bother putting the calciums and the aluminum on this chart because those are individual atoms. It looks like we need a total of 2 aluminums. So I can just now put the coefficient 2 aluminums. And then let's see, 3 times, now since there's no number after the calcium, I'm going to just put a subscript 1. 1 times 3 is going to be 3 calciums. I need to put 3 calciums over there. Because my chlorines are balanced, now my 3 calcium atoms are teamed up with the 3 calciums that are embedded in there. And I think we got everything on that one. Number 5. So when you're looking at these different types of reactions, so we've got 2 compounds forming 2 compounds, so it's not going to be decomposition or synthesis because we're not breaking down anything or combining stuff. But we're getting a couple switches because if you notice, this PO4, phosphate, over here is teamed up with aluminum. So it's like this aluminum has come over here and it's kicked off this calcium and it's going to team up with the phosphate. And this calcium is going to come over here. I kind of equate this to 2 pairs of dancers on the dance floor. And in the middle of the dance, they decide to trade partners. So the calcium is displacing the aluminum. The aluminum is also displacing the calcium. This is what's called a double replacement. So 2 compounds are forming 2 compounds, and they've traded dance partners, if you like. Or if you want to be scientific, the ionic part of the compounds have traded to get a new anion they're working with. Anyway, let's continue on. Balance and identify this type of reaction. Okay, well that's what it is. So now let's balance it. I'm going to let's get that out of the way there. Well, there is no element by itself. There is no oxygen in here. So what I'd recommend doing is kind of maybe recognizing we got an SO4 in the reactants and the products. Those stay together. I'm just going to put parentheses around. So let's see. I'm going to make the T-chart here. We'll do calciums. We have over here 1 calcium. I'll put the subscript 1. Over here we have just 1 calcium. Okay, I'm going to do, now we got the phosphates, the PO4s. Now you could break it down and do all the phosphoruses and oxygen separate, but you're just making more work. Since the phosphorus stays together, you can see it over here on that side. Sorry about that being off. They stay together. I'm just going to treat them as if they're all just one type of compound. We have 2 of the phosphates because the parentheses are telling us there's 2 of those. So I'm going to say we've got 2 of those in the reactants. Over here in the products, there's just 1 of them. Okay, and let's see now. Aluminums. We've got 2 aluminums over here in the reactants. Only 1 aluminum there. I'm starting to run out of room there. Tell you what, I'm going to just put a piece of paper down because I don't want to destroy the next one there. All right, now we're doing the SO4s, the sulfates. They stick together, and in this reaction, there was just 1 of them. Over here in the reactants, excuse me, in the products, there's still just 1 of them. So SO4, just 1. All right, so the calciums are okay. So we got to work on the aluminums and the phosphates. So since we have 2 aluminums over here, we definitely know, okay, we're going to need 2 over there. So I'm going to go ahead and put coefficient 2 here. And if it helps you, I'm going to put a big pair of parentheses out here, because now we've got 2 of these aluminum phosphates, which means we got 2 aluminums now. 2. And now we've got 2 of the phosphates, the PO4s. And let's come to this side of the equation. Oh, look it, we got 2 aluminums and 2 phosphates. Hey, 1 calcium and 1 calcium. I think we're balanced. I'll just double check. Yeah, at this point, we're done. You've got a balanced equation. Coefficient 1, 1, 1, and 2. There you are. Well, looks like this is, what do we got? 1, 2, 3. Another type of reaction we've got here. We've got a hydrogen and a carbon. We call that a hydrocarbon reacting with oxygen. But here's the main tell for you on this particular reaction. If you are making carbon dioxide and water, that is combustion. That may be the one to memorize, because some people might think, oh, but isn't the oxygen displacing this? Kind of, sort of, but it's kind of displacing 2 of them. So some people get caught in some type of a weird single or a double replacement. If it's starting to get weird and you can't really follow it, oh, hey, we're basically burning a type of fuel, and if it's burned perfectly and efficiently, you would get those 2. So it's combustion. In a combustion reaction, since we've got an O2 over here, that would be what you balance last. The O2, the oxygens. We don't have any pure metals or elements by themselves. At this point, what do you balance first? Okay, carbons or hydrogens, doesn't matter. I'm just going to, since carbon's first, I'm just going to do that. In fact, I'm going to make my T-chart here, because I think that's a good idea to help people out. If you can't just strictly do it mathematically. I'm going to erase the carbon and hydrogen there, just so we don't. So C9H18, oh, sorry, my goof. Carbons, we got 9 of them in the reactants. In the products, carbons, we just have 1. There's no carbon hiding over there, so just 1 carbon. Hydrogens, looks like we've got 18 of them in the reactants. In the products, only 2, so we'll balance that in a little bit. Oxygens, over here in the reactants, we have 2 atoms. Now, if you're having trouble with that, that is 2 molecules of oxygen, if you need a visual. And then on this side, now be careful, we've got 2 oxygens in this 1 molecule of O2. So we got 2. But then we have 1 oxygen also in the 1 molecule of water. So 1, 2, 3 oxygens. We're going to do the oxygens last. So I figure, okay, I'm gonna do the carbons. We need 9 more carbons on this side. I'm going to put the coefficient 9. I'll erase that 2 from our little work before. So now we got 9 times 1 carbon is now we got 9 carbons. 9 carbons. Cool, they're balanced. Let's go down to the hydrogens. We got 18 over here. We only have 2. 2 times what is 18? I think it's 9, isn't it? 9 times 2 is now 18. Okay, cool, we're balanced there. Oh, now we got to go back, and what I forgot was when we change these coefficients, now we got to check on the oxygens here. 9 times 2 is 18 oxygens. 9 times 2 is 18 oxygens. And then 9 times 1 is going to be 9. So the oxygens are going to be 18 plus 9. And I think when we add those up, that's going to become, what, 7 and 27. I get that right? Yeah, got it. So now we've got 27 oxygens. Over here, we've got 2. Now, here's the problem. We've got an even number of oxygens, an odd number. So here's the trick for this. When you get everything but the oxygens balanced, and there's an even and an odd number, we need to turn this into an even number, and you do that by multiplying your coefficients by 2. So what we're going to do is, right now there's only one of these molecules. I'm going to make that 2. Not going to mess with the oxygen yet. Over here, we're going to make this 9 times 2 is going to be 18. Oh my goodness, this is becoming a monster. We got to double that one. 9 times 2 is 18. So we got to go back and change some stuff. 2 times 9, okay, is 18 carbons. 18 times 1 is 18 carbons. Okay, we're all right there. And then over here, 18 times 2, well, let's see, that's going to, if it was 20, I think that's going to end up being 36, unless I didn't, yeah, I think that's right, 36. Over here, 18 times 2 is going to be 36. So let's see here. I want to make sure I didn't do that wrong. 8 and 8 is 16. Yeah, there we go. Yeah. Okay, so 36. So those are balanced. All right. This is a little bit of work here, but it's doable. 18 times 2 is now, whoa, is that going to be 8 times 2? I want to say, oh, okay. Going to get my calculator now, because if I try to do this on my head, I'm going to mess up, and I don't want to mess up. So let's see, we've got 18, what are we at? Where are we at? 18 times 2, sorry, 36, duh, okay, 36 oxygens there, and plus another 18. So 36 oxygens there, plus 18 over there, 36 plus 18 equals 54, wow. 54 oxygens. Wow, that one got big on us. But now it's doable. Because here we just have 2 still. 2 times what is going to be 54? Well, let's see. 54 divided by 2 is 27. So we need to make this 27 O2s. 27 times 2. 27 times 2 is 54. Finally, wow, 54, 54, 36, 36, 18, 18. Our coefficients are 2, 27, 18, and 18. Wow. Okay, I think the ones on your test are just a little bit easier than that one, but that's how you would do it. The trick there was, once we got everything balanced, the carbons and hydrogens, we just needed to double everything in order to get an even number of oxygens on each side. Well, that was a big one. All right, number 7. This one should go a little bit faster for us. So we've got this reaction. Now, you know what? Taking a look, let's look at this. We've got 3 times 2 is 6 oxygens. 2 times 3 is 6 oxygens. 2 irons. 2 times 2 is 4 irons. You know what I did when I made this review sheet, everybody? That should have been a 4. So let's fix that right now. Now, yeah, I know you may be groaning because you goofed up because of that. Sorry, but we got it corrected here. Let's see. Label the reactants and products, okay? Reactants are the ones that are mixed together. I'll just label them R, and those are products. Let's see, what does the arrow represent? That means changes into a chemical change, yields, makes. Okay, it's like an equal sign though, because you got the same number of atoms over here as over there, and that's why I had to fix that because I goofed. How many molecules of O2? Okay, so there are 3 molecules of O2. On this, that coefficient's telling us there's 3 molecules. Now that I've corrected it, okay, we need to put 4. How many molecules of Fe? Well, they're only in the there's, and really, okay, they're technically not molecules. They're going to be just atoms because they're not bonded together. So And then over here, rust, the Fe2O3, well, we've got a coefficient 2 in front of that, so we've got 2 molecules of that. So be careful on the test, because we may ask you number of molecules, or this one. In the reactants, okay, we're just looking over here, how many atoms of oxygen? Well, there's 3 molecules of O2. Every molecule has 2, so 3 times 2 is 6 atoms. In the reactants, now that we've corrected it, there's 4 atoms over there. If you had a 2 there, okay, you fix it because I goofed up there. Number 10, in the products. Now we're looking at the products. Now, this is a balanced equation. How many total atoms of oxygen? Well, there should be 6. Let's see. 3 oxygens in 1 molecule, but we've got 2 of them. 3 times 2 is 6. And then the irons, 2 times 2 is 4. And look at the number of oxygens in the reactants equals the number of oxygens and irons in the products. That's a balanced equation. Label what you should balance first and last in these reactions here. Let me zoom out a little bit. Okay, balance first. You should do the aluminum first. And then, take that back, and not fist. We should do the aluminum last, because it's an element, we want to do it last. So then obviously we have to do the oxygens first, in this case, since that's the only one left. By the way, we've got 2 different compounds or elements changing into just one. This is a combination. Over here in this reaction, okay, let's see. We need to balance that first. Okay, so, this is one we had up above, so that's what we'd recommend you doing first. Then you can either do the carbons or the hydrogens next in that one. All right, label the names of the 3 and 2 in this. Now, this was another goof up. I'm just going to make that back into a 4. So label the names of the 3 and the little 2 on the oxygen gas molecule. Okay, we're just focusing on this one. Well, the 3 is called a coefficient. That's a multiplier. It tells you number of molecules. There's 3 molecules of O2. Molecules. Yeah, I can't read it. Well, you can write. And then the little 2 right there, that's called a subscript. Subscripts tell you number of atoms. And in a chemical equation, when you have a balanced equation, you just add up all the subscripts, and they're going to add up, or you might have to multiply them by the coefficient, but that'll tell you how many you've got. Explain what each number means. Okay, told you, multiplier, number of atoms. Are you allowed to change it when balancing? You may change coefficients, yes. Subscripts, no. You may never change the subscripts, no. The video I suggested for you to watch, they put a little skull and crossbones on those. I know that looks kind of like a weird, unhappy, sick pig, but you may not change the subscripts. You can change only the coefficients. Draw and diagram this reaction. Okay, well, we've got 3 molecules of O2, so I'm just going to draw O2 like this. Okay, we've got 3 of those. I'll label that O, O, and O. And we've got 4 atoms of iron. Now, iron's going to be a little bit bigger. 1 iron, another iron. Now, these are not touching each other. If we touch these together, that means that they are reacted together. So here's what we've got in our reactants. And now these are going to combine. The iron's going to team up with the oxygens, but we're going to get 2 irons. So 2 of these irons are going to team up together, and they're going to be connected with some oxygens. You don't need to worry about the exact form of where they go, but there's 3 oxygens. So here's one of my rust molecules, and then we need another one because we've got 2 of those. So the other 2 Fe's team up. And if it really bugged you, you can go online and you can look up what the actual structure is. I just want you to know, I don't want those to touch. There we go. We've drawn that. It's enough on this for part one.